This video will walk you through my exploratory analysis of the breast cancer diagnostic dataset. The main goal here was to figure out which tumor characteristics are most useful in telling apart malignant from benign cases. This dataset comes from Kaggle and belongs to the healthcare industry, more specifically, cancer diagnostics. The target variable is diagnosis, which is encoded as either malignant or benign. The features fall into three categories: mean measurements, like radius, mean, or perimeter; standard error measurements, which tell us about variability; and worst measurements, which are basically the largest values recorded for each feature. This dataset contains 569 rows and 32 columns. In other words, there are 569 records and 32 different features to consider. Of the 32 features in this dataset, all are numeric except for the target variable, which is the diagnosis. Although this dataset was already cleaned, I double-checked to make sure there were no missing values or duplicate rows before starting the analysis. Here is the breakdown of our target variable. We can already see that benign cases outnumber malignant cases. More specifically, there are 357 benign cases that make up roughly 63% of the dataset and 212 malignant cases that make up 37%. When we look at correlations between the mean measurements and the diagnosis, some trends jump out. Size features like radius, perimeter, and area have the strongest positive correlation with malignancy. Shape irregularities like concavity and concave points are also strong indicators. Features like smoothness, symmetry, and fractal dimensions are less informative on their own. Standard error measurements generally have weaker correlations, except for area, radius, and perimeter, which show moderate strength. These tell us that variability in size can be somewhat helpful, but not as much as the actual measurements. Now this is where things get a little bit interesting. Worst case values like radius, perimeter, and concavity have the strongest overall correlation with malignancy. In other words, this suggests that if a tumor has an extreme measurement, it's more likely to be malignant. Looking at distributions by diagnosis, size-related features are right-skewed, with malignant tumors generally having higher values. Texture, smoothness, and symmetry have more overlap, meaning they're harder to use for classification on their own. Standard error features are more symmetrical overall and have a lot of overlap between benign and malignant cases. The exception is variability in size, such as area, radius, and perimeter, where malignant tumors tend to show more variation. Here, we can see that worst measurements tend to mirror the mean measurements but at larger values since they're maximum. Again, size and concavity related features have the clearest separation, while smoothness, symmetry, and fractal dimension overlap a lot between classes. In conclusion, the most predictive features are size and shape irregularities, especially their worst case measurements. If I had to rank measurement types for predicting malignancy, worst cases would come first, then mean, and finally standard error. We also saw that many features are right-skewed and highly correlated, so normalization would be recommended on the dataset if we were to move on to modeling.